Hi all! This episode of Physical Attraction is brought to you by the American National Standards Institute. Standards make the world go round, and they also dictate what is round. Without standardised measurements and definitions, physicists would be speaking to each other in different languages and would struggle to understand the universe even more than we already do. You can learn about standards in America at the ANSI blog at blog.ansi.org/pod to learn about how standards apply to you. Now on with the show.
Into his eyes. They're the eyes of a man obsessed by sex. Eyes that mock our sacred institutions. Bedroom eyes, they called them in a bygone day.
Hello, and welcome to Physical Attraction, the show that explains physics, one chat-up line at a time.
But for corrupting others to a life of carnal pleasures and lewd designs. A man whose erotic desires and libertine practices are used to titillate the unsuspecting and would stoop to any depth.
Hello and welcome to Physical Attraction, where we're about to launch a series of episodes on atomic, molecular and subatomic physics. This first episode I've given the rather ludicrous title of Up an Atom, Dank Memes and Atomic Physics. Can you tell your quarks from your elbow? If not, never fear, because these episodes will be your guide to particle physics, and specifically what's called the Standard Model. Now that has absolutely nothing to do with the catwalk. Soon we'll get into particle physics beyond the Standard Model, but before that we need to do a recap of atomic physics in the first place. Once we get to beyond the Standard Model, well then the innuendos will really start to fly. Let's begin at the beginning. In 1936, particle physicists felt pretty pleased with themselves. They discovered the three major component particles that made up the atom, the neutrons and protons in the nucleus, and the electrons that orbited around the nucleus, and they're in the process of measuring the properties of these particles. This was a really exciting time, because who knows what kind of technological applications and scientific understanding could be gained now that the fundamental building blocks of matter were observed and catalogued. We would surely get an understanding of, well, more or less everything that could be understood. Then some physicists, Carl Anderson and Seth Niedermeyer, noticed that there was a particle in cosmic radiation that they couldn't explain. It curved in a magnetic field, so it was a charged particle. It felt electromagnetic forces, so it must have an electrical charge. What is charge? Well, you can get a bit hung up on the definition. I think it's helpful to think of it a little bit like an electrical mass. The mass of an object tells you how much gravity pulls on it. The charge of an object tells you how much the electromagnetic force pulls on it. So the new cosmic ray particle was charged. But it didn't curve like an electron. It didn't curve like a proton. You have to remember that they're looking at these particle tracks in cloud chambers and bubble chambers. So every new subatomic particle leaves a different, distinct track. And this one was unlike anything they'd ever seen. They'd discovered something new. And before too long, the young physicists involved had won a Nobel Prize, and the particle they'd found, the muon, was being studied as a whole new field in itself. But it completely upended the model, the theory, that particle physicists had about what existed in the universe. So much so that when the physicist I. Rabi, who would later have a Nobel Prize of his own, heard that the muon had been discovered, he quipped, "Who ordered that?" Later, the physicist Willis Lamb in 1955 joked that back in the day, discovering a new particle was rewarded with a Nobel Prize. But now, it should be punished by a $10,000 fine. Particle physics is a strange field for people who want the world to be neat and orderly. There are dozens of different fundamental particles, so much so that they're often referred to as a particle zoo. A whole zoo of animals, strange, subterranean beasties. Physicists, in fits of creative ecstasy, have given them exotic and amusing names. The strange quark, the electron neutrino, the tau particle. But many of these particles don't last for very long. The muon, which only exists for 2.2 millionths of a second, is considered pretty stable compared to some of its fellow subatomic particles. By the way, 2.2 millionths of a second, or 2.2 microseconds, it's also the exact length of your good mood when you wake up on a Monday morning before the grim horror of reality dawns once again. And particle physicists are also very strange creatures. They love things to be neat and tidy, and organising their zoo into little families and groups in a way that they can understand. They want a standard model that will explain all of the different properties of these particles. But they also love nothing more than to spend billions of dollars smashing particles together at ridiculously high energies, creating massive cascades of subatomic particles as debris from the collision, in the hope of making new things to scratch their heads over. Things that don't fit into any family or categorization, but more deeply and more philosophically, things that are quite inexplicable. I mean, if the particle doesn't make up ordinary matter, if it's incredibly rare and only appears under certain circumstances, and if it only lives for a tiny amount of time in the wild, why should it exist? In a universe that was created by an intelligent designer, you think he'd have an inordinate fondness for these short-lived particles. Either that, the particle physicists think, or in some fundamental way, they're all necessary to create the physics of the world around us. But when these things were first discovered, like the muon, there's no way that people could understand why such a thing would exist. And since then there have been plenty of particle discoveries that don't seem to make an awful lot of sense. Things where we can legitimately question, who ordered that? So first off, I'm going to try to explain the standard model of particle physics. Now, the standard model is effectively, as far as the theory has advanced so far, in a way that people universally accept. There are plenty of particles that don't fit into the standard model of particle physics, but not all physicists accept that these exist. So I won't treat them in the same way. But then there'll be a future episode where we'll talk about possible developments beyond the standard model, a field of study which is literally abbreviated as BDSM. But of course, before you get into BDSM and the particles we haven't seen yet, you need to understand ordinary vanilla particle physics. And for that we really need a history of atomic physics. So let's make sure that we're all on the same page here. Everything in the world around us is made up of molecules. For example, water is a molecule. Molecules themselves turn out to be multiple atoms bound up together. So water is 2 atoms of hydrogen bonded to 1 atom of oxygen. And there are different types of bond. There are covalent bonds, where atoms, broadly speaking, share their electrons together. And there's ionic bonds, where the electrons are exchanged. There's also some different bonds you need to think about, like hydrogenic bonds, but we won't get into that too much. Atom theory has a long history, stretching all the way back to the Greek philosopher Democritus. He's usually credited as being the first one to propose that everything was made up of tiny, indivisible parts, and to relate the properties of the whole to the properties of these atoms that made up the whole thing. Democritus was known as the laughing philosopher. Apparently he was constantly mocking others and laughing at human folly. He sounds quite annoying. So I feel like we're well within our rights to laugh at him because his theory was far from correct. He thought that water was slippery because water atoms were very slippery, while iron atoms were very hard. And of course we know that this isn't the case at all. But Democritus gets some credit for suggesting that things aren't an elemental continuum. Because although it's tempting to laugh at this man who was called the Mocker by his fellow citizens, let's face it, his real nickname is probably much worse if he spent all his time criticising them, he did realise something that's incredibly counterintuitive. Even today you can see people on some of the darker fringes of the internet saying that, well, of course there's no such thing as an atom, no one has ever seen one. It sounds like you're taking it on faith. And while that's patently false, it's true if you're talking about naked eye vision, atoms are too small to see. The world around us appears to be made up of elements, such that if you were going around you'd pick up on it, right? This is air stuff, this is water stuff, this is plant stuff, this is rock stuff. You can see why the natural division of things by the Greeks and so on was into air, earth, fire and water, because these were familiar elements, and yet it turns out that actually none of those is an element. If you characterise objects by their macrophysical properties, the properties that they have on the scale of things that you can see, then it doesn't make sense to lump together some of the things that we have to. If you take mostly carbon, hydrogen, oxygen and some traces, well, you can get wood or you can get people. Just carbon alone can give you either graphite, which is a soft, electricity-conducting, opaque rock, or diamonds, a hard, shiny, transparent, electrically resistive substance. Yet both of these substances are made of more or less precisely the same thing. All that differs is how they're arranged in the crystal lattice. So it's not immediately obvious that things are made up out of the elements that they're made up out of. And of course things get worse because most of what we're familiar with is compounds. We very rarely see elements in their pure form. So there's really not that much of a basis to go on to say, oh, it's obvious that things depend on the properties of their atoms. So Democritus was right to point to atoms, but he was wrong in deciding that the properties of a substance were entirely down to the properties of the atom itself that had the same properties. After all, we know that a hydrogen atom is equally happy to be a part of water, H2O, or making up oil in hydrocarbons. It's all about the chemical bonds between the atoms. There were different kinds of atoms, and scientists in the 18th and 19th century were beginning to realise that there were some substances that were in a sense fundamental. They could react with each other, and things could be broken down into these elements. But you couldn't transform elements into each other, and you couldn't turn them into anything else without mixing in another element. It was an examination of chemistry and chemical reactions by John Dalton that really gave convincing scientific evidence for atom theory. He noticed that when he was combining these elements that they'd known about, there was a pattern in the way they combined. So for example, when they were mixing nitrogen and oxygen, the nitrogen could absorb a certain amount of oxygen, or twice that amount, but never anything in between. So it's strange. You'd think that you'd be able to mix together nitrogen and oxygen in whatever ratio you want. But actually, of course, it makes perfect sense when you realise that you're either seeing a chemical reaction into nitrous oxide, NO, or nitrous dioxide, NO2. What's happening is that the atoms of nitrogen and the atoms of oxygen are joining together. If you're producing nitrogen dioxide, then you have to pair one atom with nitrogen with two atoms of oxygen. There must be fundamental units of each gas that can only combine with each other in whole numbers. So mathematically you'd call it discrete rather than continuous. And this is why you could only mix certain amounts of nitrogen with certain amounts of oxygen to produce certain amounts of product. Dalton himself came up with atomic weights, and it was noticed that they also had a great ratio relationship going on, because everything wound up being roughly multiples of the lightest element, hydrogen. So physicists began to propose the idea that the atoms of the heavy elements were made up of multiple hydrogen atoms. This sounds reasonable, of course, but it's not quite right. And this is where you need to understand that physics is a dank meme. Specifically, it's that one, the expanding brain meme. Either you know exactly what I'm talking about, or you haven't a clue, so I'll explain for the benefit of people who haven't wasted much of their lives. In this meme, which is just a simple image that's shared on the internet, you have a series of artistic images of a human with a brain. Alongside them are captions that relate to some topic. The first image is a small brain inside the skull, and the caption is some simple observation. The second image, as you progress deeper into the meme, the observations get more complex and the picture gets more elaborate, first with the brain lighting up, and then with rays of light shooting out of the brain, eventually with some kind of godlike figure having attained some incredibly high level of understanding. Here's an example. Physicists who use numbers, physicists who use letters, physicists who use Greek letters, physicists who use tensor notation. Yet this meme is all of physics. Physics is this meme. It is a series of explanations for reality that get gradually more advanced and detailed as you go along. In some ways, talking about whether it's wrong or right misses the point. All models of reality are wrong by necessity, but some models are useful. For example, consider something like plate tectonics. That wasn't accepted for a very long time. But what it could do, that other models couldn't, even though it seemed ludicrous to a lot of people at the time, what it could do was explain things that had happened in the past, and even predict things that were going to happen in the future. That's what made it a good model over other theories. You can come up with a wonderful model, if you like, that explains all the properties of things that currently exist. And if it can't explain new information that's added into the model, or things that will happen in the future, then it's not as good as a model that can explain those things. So, returning to the dank meme of physics, or at least atomic physics, in this example, maybe we'd have the first caption as everything is made up of fire, air, earth and water. And then we'd have the second caption as everything is made up of indivisible elements. And then we'd have everything made up of indivisible atoms. And soon we'll have that the atom is actually made up of electrons, neutrons and protons. And then the standard model that explains what each of these are made of. And possibly after that, we might have string theory, or quantum field theory, or loop quantum gravity, some other theory of everything that goes beyond the standard model. Each layer allows you to understand more, but it also grows more complex. And perhaps none of them is truly correct, truly the actual nature of reality. That is very difficult to understand. But some of them are incredibly close approximations to reality, that can predict what we see in the world around us. And that's as close to truth as we're ever going to get. Okay, enough meme tangent. Meanwhile, in 1897, the physicist with one of the coolest names of all time, J.J. Thompson, was investigating cathode rays. So people had noticed that as soon as they were able to produce good vacuums by pumping the air out of glass containers, something weird happened if you tried to pass an electrical current through that vacuum. We're going to do some episodes on Isaac Newton. You may have already heard them by the time you listen to this episode. And you'll remember that one of the things Newton was concerned about was how light was still able to travel through a vacuum. He had a corpuscular theory of light, this idea that light was made up of lots of tiny little particles. And yet it concerned him because light could travel through an evacuated chamber as well, which made him think that maybe light was sort of like a wave, not like a particle, because surely all of his light particles would have been pumped out of the glass container as well. Well, there was a similar concern over cathode rays as late as 1897. So imagine you've got a tube with a glass container that's been completely evacuated. Then you have different electrical charges on different ends of the tube. Two electrical conductors, one is positively charged, it's called the anode, and the other is negatively charged, that was called the cathode, which is why these are called cathode rays. The behaviour of these cathode rays depended on how well you evacuated the tube. If the tube was partially evacuated, you could see sparks, or a glowing beam between the anode and the cathode. But as vacuum pumps got better, they were able to pump more and more air out of the tube. The scientists noticed that there was a dark spot that appeared in front of the cathode with no glow. And as you pumped more and more air out of the tube, that dark spot grew until it filled the entire tube. But at the anode end of the tube, the glass itself would glow. So it's strange. You can't see the sparks anymore, but you can see a growing dark spot, and then eventually, at the far end of the tube, the glass glows. The conclusion was that something invisible was travelling along the tube, carrying the charge, and interacting with the anode end. The circuit was complete, but they couldn't see what was completing it. These were called cathode rays and had been studied for decades, but JJ was able to measure the mass of the cathode rays, and he found that they were over 1,000 times lighter than atoms and negatively charged. What's more, regardless of what material you used as the cathode or anode, these corpuscles were exactly the same in mass and charge. Whatever cathode rays you were producing were the same regardless of what elements you used in your detector. Cathode rays could be made from all kinds of materials. So J.J. Thompson proposed that these particles must also be a part of atoms. Thompson wanted to call them corpuscules, showing that despite having a cool name himself, he had no idea about naming particles. But the name that stuck was electrons. After all, electricity. So we're getting closer to the truth of what the atom is. Physicists by 1904 had figured out that it must contain some negatively charged electrons, and also some positive charge as well, because atoms were overall electrically neutral. They weren't deflected by electric and magnetic fields like charged particles were. And they noticed, of course, that when you produced cathode rays from a material, knocking away the negative charge, there was some positive charge left behind. So clearly atoms were a mix of positive and negative charge that exactly cancelled out, making things overall neutral. But physicists still hadn't discovered the proton. Instead, they thought that perhaps the atom was a positively charged lump of matter, with some spread out electrons embedded in it to keep the charge neutral overall. This is called the Plum pudding model, although in Thompson's case he correctly figured out that the electrons must be orbiting in some way. The plum pudding model had some obvious problems, and it wasn't universally accepted. For example, if you have a plum pudding model, then you might imagine that there would be some concerns over the charge distribution on the atom changing as you go around it, because you're approaching the position of an electron, or not. Hantaro Nagoka, for example, was a Japanese physicist who suggested an alternative model, where the electrons orbited the heavy central positive charge like the rings of Saturn. That way they could always effectively screen the charge from the outside world, leaving things electrically neutral. This is closer to the truth, but the astonishing aspect of atomic physics hadn't yet been realised. The plum pudding model was blown out of the water by the famous experiments conducted by Ernest Rutherford, Hans Geiger, and Ernest Marsden. They wanted to use radiation to probe the structure of matter. Listen back to Unusually Hot, the old episode, where we discuss all the different types of radiation. The kind that they used were alpha particles. As we discussed then, alpha particles are helium nuclei. They have 2 protons and 2 neutrons, and therefore they're positively charged. Beta particles aren't just alpha particles that don't work in finance and own shabbier cars, they're electrons too. The confusing names in physics all tend to arise from misunderstandings like this, because when the beta particle was discovered, people didn't know they were electrons and they didn't have names properly, so it gets confusing. But anyway, alpha particles, helium nuclei, 2 protons and 2 neutrons. In Thompson's model of the atom, the positive charge is spread out or diffused across the atom. Geiger and Marsden set up the experiment to bombard some gold foil with alpha particles. Now in your high school physics class and mine, what you often hear is, and then all the alpha particles flew straight through the gold foil, confirming that the atom was mostly empty space. But this isn't what really happened, because Geiger and Marsden already knew that the alpha particles could penetrate through layers of thin foil. That's why they made the foil thin in the first place. The point was the idea that you could measure the charge distribution on the atom by seeing how much they were deflected. They'd done the calculations, and they had their expectations, which is always what you should do when you're doing a physics experiment. You should know what you're looking for, and you should know what you expect. And then if it's different, then you understand that you're looking at new physics. What they were expecting to see were tiny deflections on the alpha particles that pass close to the atoms. The positive charge on the plum pudding atom would repel the alpha particle and deflect it by a small amount. The really crucial thing that they observed wasn't that many of the alpha particles went straight through the foil. They knew that already could happen. But instead, the really amazing thing they saw was that some alpha particles were deflected by ridiculous degrees and shot out at right angles, or even sometimes right back at the radium sample that they used as an emitter. They had as a detector set up a ring of fluorescent paper. The only way you could see the alpha particles was from a tiny flash when they hit the detector paper. Rutherford was a wily old dog, and he left the laborious job of counting these flashes, which took hours, to Geiger and Marsden. Perhaps this experience of manually counting particles motivated Geiger to develop his Geiger counter for automatically counting radiation. But they must have been motivated in this by what they saw on the near side of the ring. That occasional, impossible flash. When Rutherford found out, he uttered one of the most famous physicsy quotes. He said, "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper, and it came back and hit you." What Rutherford realised is that their model of the atom was completely wrong. There must have been some head-on collisions where the alpha particles were essentially directly striking something that was very small, hence the low probability of a deflection, and very densely charged. It's important to understand that the electric field at a surface depends on the density of the charge, its concentration, and not the total amount of the charge. So you can get these mad deflections of 90 degrees or more, providing you have a very powerful electric field that's concentrated in a very small area. The spread out, diffuse positive charge of the plum pudding model could never do that. The electric fields never quite get big enough to kick you all the way back on yourself. This experiment allowed Rutherford and his colleagues to estimate the size of the small, positively charged nucleus at the heart of the atom. Rutherford realised that it was so small you could effectively treat it as a point right at the heart of the atom. And we now know that, depending on the atom, the nucleus is 20,000 to 145,000 times smaller than the atom overall in length. In terms of the volume it takes up, you have to cube that. This is what leads to all of those great analogies, like if the nucleus was a pea, the atom would be the Sistine Chapel and mostly empty space, or whatever. Here's one I worked out. If the nucleus was a golf ball, the hydrogen atom as a whole extends across more than 5 golf courses. So in Rutherford's model, the electrons orbit the central, tiny, positively charged nucleus. They're pulled in by the attractive electromagnetic force between the electrons and the nucleus, just like planets orbiting the Sun. In this case, electromagnetic force, not gravity, provides the force towards the centre that allows them to accelerate and zoom around the nucleus. And later, physicists would discover that the nucleus was made up of the positively charged protons and the neutrally charged neutrons, which in some ways acted like a glue sticking the whole thing together. Finally then, we have a good model for Democritus's atoms. The indivisible proton, neutron, and electron, and in various combinations you can add up these fellas to make any element you like. This picture of electrons whizzing around a nucleus, although it's never drawn to scale because then you'd never see the nucleus, is one of the most familiar images in all of physics. It's also completely physically impossible. Physicists already knew at that time that if you have an accelerating charge, it radiates energy. We discussed this in our episode on electromagnetic radiation. Do you remember the wiggling electrons that produce the light that we see in the world around us? And of course this same phenomenon causes the northern lights, the aurora borealis. At this time of the year, under these atmospheric conditions, localised entirely to your kitchen. But the northern lights, the aurora borealis, they're charged particles from outer space. They produce that wonderful glow when they're accelerated in the Earth's magnetic field, because accelerating charged particles produces light. That glow is energy. But there's a very scary question there. If these electrons are orbiting around the positively charged nucleus, they're constantly being accelerated. They should be radiating, which means that the electron should be emitting energy constantly, which means it should be losing energy, which means it should spiral into the positively charged nucleus and decay, which means that atoms aren't stable. And when you do the calculation, they're really not supposed to be stable for very long at all, which means they can't exist. But they do, so what the hell is going on? The answer to this question is quantum mechanics. And yes, we will get there soon. But I really want to lay down the foundation of classical physics first so I can refer back to it and explain how quantum messed everything up. But I hope you're beginning to see why physics is an expanding brain meme. You start with Democritus's atoms, then you get an idea that atoms are maybe made up of particles themselves, and then eventually you think you've got it with the nice Rutherford model of electrons zooming around a tiny nucleus. And that's as far as a lot of people get. But it's still not quite right. This is why physics is an expanding brain meme. There are layers and layers, and we're still not at the bottom. Thanks for listening to this episode of Physical Attraction. Next episode we're going to get onto the full standard model of particle physics. By the end you will be a fully clued up particle physicist. You're not going to want to miss it. You can finally understand what the LHC is going on about if you didn't before. Until then, there's plenty of things you can do to stay in touch with us. We're on Facebook, Physical Attraction. You can follow us on Twitter, @PhysicsPod. There you can donate to us via the PayPal link. If you're on Twitter, which is of course a cesspit of things that are both wonderful and brilliant and terrible and all kinds of different things, then you can ask questions and I'll answer them on the show. If you don't want to sully yourself by going on Twitter or completely ruin your productivity, then you can go to www.physicspodcast.com. That's www.physicspodcast.com. I feel like it's quite memorable. And there you can comment on any show, and if you put any comments on any shows, I will listen to them, I'll take them into account. I want to make the show better for everyone, so you can help me in that. And if you have any questions that you want me to answer, if you have any topics that you want me to do shows about, that's the perfect place to put them. You'll also find there, under the donate section, a PayPal link where you can donate to the show, help us keep going. It takes a lot of time, takes some money for me to do hosting costs and so on, pay for microphones, coffee, that sort of thing. Even just $1, the price of a cup of coffee wherever you are. I think the shows that you've listened to so far are worth that, and it would really help us out. But if you don't want to do any of that, then one of the best things you can do is rate and review us on iTunes. I'll shout out your name on the show. Or just tell one other person about the show. Because if everyone listening tells just one other person about the show, well, within 30, 40, 50 episodes, we'll have over 1 trillion listeners. And I really think that would be amazing. Until next time, be kind to each other.
Pornographic